Institute, and we're going to record this meeting for record-taking purposes, and want to welcome everyone to today's webinar. I appreciate coming on, no matter where you are in the world. I know Faye's here at 1 o'clock in the morning. Neil, I'm sure it's the evening there where you are. So we do appreciate the commitment of everybody making the time to be here, and hope to have a productive day for you today. Next slide. We always try to go over some guidelines very quickly in order to maintain bandwidth on the communication. But you've seen these all before, so we want to get to the technical part of today's agenda. So real quickly, just remember to mute your mic if you're not speaking, turn your camera off to preserve that bandwidth. Do whatever it is that you do to be present and multitask in these kind of environments. We understand that everybody's got their own approach, and we want to support you in that. As we go through today, we'll have facilitation on panel questions, and we're going to prioritize panel questions today. That's really a big part of today's deeper dive into some of these questions. We're going to monitor the online chat feature just in case, to keep track of other questions that we can get to you. I doubt we will, but we look forward to a full discussion. So don't hesitate to chime in there. So we always want to close by saying on these meeting guidelines and say thank you for supporting NWRI and meeting in these sorts of environments. Thank you so much. Next slide. I want to do a few introductions for today. We got a lot of people on the line, but I want to recognize the folks who have been supported this project and supported NWRI so thoughtfully. I want to start with our independent peer review panel members. Our chair, Gordon Zhang. Gordon, welcome. It's good to see you again. Happy New Year.
Thank you.
We also have, as our members of our panel, we have Neil Bonas from the University of Strathclyde. Neil, welcome. Happy New Year.
Happy New Year. Good to be here.
We also have Faye Chai. Faye, thank you for joining us so early in the morning where you're at in China.
Hello, everyone. Good to see everyone. Happy New Year.
Marjorie Fredericks from the Virginia Institute of Marine Sciences. She's on her phone, so I won't make you unmute. Margie, we know you're there. Thank you for joining us while you're traveling. Let us know when you're able to jump on. Perhaps Alex has joined us. I don't know, because I can't see the whole group yet. But Alexander Kurapov from NOAA is a member of the panel as well. And I do see Mike Stukel on, and Mike from Florida State University. We were a little concerned about the weather in Florida today. But Mike, welcome and Happy New Year.
Hi, everybody.
Next slide. I also want to take a minute to introduce the panel steering committee members. I don't think all of them are online, and we won't check in with them, but I did want to recognize the 6 members of the project steering committee: Lorian Fono from the Bay Area Clean Water Agencies, David Gibson, who's the Regional Water Quality Control Board Executive Officer in the San Diego region, Justine Kimball, who's on the staff at the Ocean Protection Council, Karen Mogus, who's the Deputy Director of the State Water Resources Control Board's Division of Water Quality, Steve Wagner, a gentleman I've had the pleasure of knowing for many years at the Goleta Sanitary District, which is in the Santa Barbara region, and Lan Weiborg from the Orange County Sanitation District. I want to thank each of them for their commitment. We'll talk about what that commitments look like in just a minute. But that committee's also been supported by 3 ex officio science advisors whose input has been very helpful for me as we've moved through this process. I want to recognize Sean Bothwell from the California Coast Keeper Alliance, Kristen Davis from the University of California at Irvine, and Steve Weisberg, the Executive Director of the Southern California Coastal Water Research Project. Thank you all for your support of NWRI in this project. Next slide. The goals of this independent review are to assess model readiness, to answer management questions, to advise on model uncertainty associated with addressing management questions, and recommend next steps for improving model readiness. This is important to the project steering committee that we kind of start each and every meeting with a review of the goals of why we're here. So here are the goals. Next slide. And where have we been and how have we gotten here? What's this process look like? The steering committee that I just introduced met for the first time on June 22nd this year. We had our panel seated by October 25th, and I picked that day because that was the day that Gordon agreed to be the chair. And we all participated in webinar 1 back on December 12th and had a productive meeting at that time. So we got to hear perspectives from the regulated and regulators and the regulated communities. We were able to hear introductory presentations on the model, and that leads us to today's webinar. And both of these webinars are intended to prep the panel to have a productive live meeting in Orange County coming up next week. So it's right upon us, this live meeting. And ultimately, the output of this effort will be a panel report that we should be in the area of producing it by the end of February, the first part of March. The panel should be able to come up with a report presenting its consensus findings and recommendations on the questions that have been presented and other issues that they see are related to the goals of the review. Next slide. So here's our objectives today. We're going to review the development setup and validation of the individual ROMS and BECs elements of the coupled model. We want to review development setup and validation of the biological conversions and the interpretation of the model outputs. And importantly, we want to provide time for the panelists, stakeholders, and modelers to engage in facilitated question and answer periods. So we'll work diligently to make that happen today on time. Next slide. Here's our agenda, and I'm running out of time here, so I don't want to go through this again, but here's where we're going to go today. As we start thinking about our agenda today, I want to let everyone know that we'll be a little bit more assertive in facilitating today, primarily because I want to make sure that for each element of the presentations that we have sufficient time for well-developed Q&A on that subject. So to help me do that today, I've enlisted the help of Martha Satula, who's the leader of the modeling team, and Martha's here today, and she's going to work with us to introduce each of these distinguished folks who are here to tell us about their piece of this coupled model and to begin the panel's deeper dive. So with that, Martha, I'm going to hand it off to you to introduce your team members and to get us off and running on our technical presentations for today.
Great. Thanks, Kevin. So it's always great to introduce myself to this audience as, either cat herder in chief or science communicator in chief. But, there's a cast of characters that you'll be meeting over the next several weeks who are the principal leads of this modeling effort. And so just to kind of give the whole audience, including the panel, just kind of a quick roadmap in terms of what we have already presented, what we're doing today, and then what you'll see next week is in our December webinar. I introduced the topic by giving an overview of our modeling science program and really a roadmap to our published works. And that was really intended for the science panel to get a good feel of what they may want to be paying attention to. Today, we're going to be talking about how were the tools developed? How were they developed, validated, and not only the numerical models, physics and biogeochemistry, but also our biological interpretation tools. And then finally, next week, we're going to be talking about how those tools were specifically configured in order to apply them and what additional validation was done to investigate the effects of land-based inputs. So today, what we're then focusing on is really these tools, the regional ocean modeling system, that's the physical circulation model, the biogeochemical elemental cycling model, or BEC, that's essentially our research grade water quality model that helps us understand how nutrients are being processed in this system and how that eventually affects things that we're concerned about. And then the last piece are the biological tools. And so I want to introduce to you today the leadership on our team that represents all of the expertise behind the ROMS model, the biogeochemical elemental cycling model, and how we interpret those seawater changes in chemistry into biological effects. So I'll start out with Dr. Jim McWilliams, who's a UCLA Louis B. Schlichter Professor of Earth Sciences in the Department of Atmospheric and Oceanic Sciences and Institute of geophysical and planetary sciences. His primary areas of scientific research are the fluid dynamics of Earth oceans, atmospheres, both their theory and computational modeling. And he is a co-creator of the regional ocean modeling system that you'll be hearing about today. His honors include being named as a fellow of the American Geophysical Union and a member of the U.S. National Academy of Sciences. Dr. Curtis Deutsch, who you see in the middle, and you'll meet him soon, is a professor of geosciences and the High Meadows Environmental Institute at Princeton University. He models the interaction of oceanic nitrogen and carbon cycles and the Earth's climate system. He's also the principal developer of biological tools to interpret changes in deoxygenation and warming of marine biodiversity. And his honors include investigator awards from the Moore Foundation and being named as a Cabell Frontier Science Fellow by the U.S. National Academy of Sciences. And then rounding out the morning, we'll be hearing from Dr. Christina Frieder, who is a senior scientist in the biogeochemistry department at SCORP, and she specializes in biological impacts from and the ocean-based solutions to climate change. Her research efforts focus on interpreting lab field and modeling data into mechanistic interpretation frameworks focused on biological effects. She received her PhD from Scripps in 2013, held postdoc positions at USC and UCI, and she joined SCORP in 2021. So with that, I'd like to kick off our scheduled talks. Dr. Jim McWilliams will be leading off, just giving you a brief overview of ROMS, followed by Dr. Curtis Deutsch to talk about BEC, and then Christina will round out the morning to talk about our biological interpretation tools. So I'm going to, with that, ask Jim to come on camera if he isn't already, and then I'm going to be running his slides for him. Jim.
Hello.
Okay, great.
I'll start by suggesting that Kevin changed the name of ROMS on his introductory slide. In the 1990s, computational oceanography was beginning to be a growth business, following in the path of computational meteorology. The models were essentially in two classes: highly idealized process depictions that were physics informative, but highly unrealistic, and global general circulation models with coarse grids, which attempted realism, but fell rather short. I was involved in helping create the first in-car ocean GCM for a couple climate studies as part of the community climate system model, now the community earth system model. But I was unsatisfied with its lack of realism. Something else was needed, so I started on the path of what became ROMS next. And so essentially there were design goals that provided the blueprint for where we went. Computational model, of course, fluid dynamics, of course, but with the purpose of depicting highly turbulent flows, which is the nature of the ocean. That is not to be trapped in the weak broad currents of global GCMs. It needed accurate and efficient algorithms beyond the practice at the time, especially for the key processes of advection, dissipation, and time integration. It had the intention of being capable of going down to arbitrarily small scales in circulation phenomena, of course, limited by computer affordability, and where the model resolution could not go then with the necessary parameterizations of the missing processes, but to have as few parameterizations as possible. In order to be affordable with turbulent flows, it had to restrict the domain, and so the practical problem of open boundary regional boundary conditions for such domains and subdomain nesting in coarser parent models. And this turned in essentially to a mandate for being able to do iterative nesting, so step by step down to smaller and smaller scales locally. That it would be realistic in the sense of having appropriate forcing, bathymetry, and the necessary physical processes, and that it be capable of online coupling to other models, the atmosphere, the biogeochemistry, surface waves, sediments, and sea ice. Next. So what I want to go through as a way of describing the contents of ROMS is essentially to give you an evolutionary history of the first steps for various pieces. The first step, you could say, was actually in the context of NCAR's global climate model. That is a vertical mixing parameterization that was designed in particular for the top and body boundary layers, which are important elements in the forcing and dissipation of the ocean circulation and biogeochemistry, for example, through gas exchange. And these processes will never be adequately resolved in circulation models, and therefore they must necessarily be parameterized. And then, of course, interior mixing, where, for example, internal waves break. The sort of first deliberate ROMS piece was to sort out alternative advection algorithms for momentum and material concentrations, because this really is the dominant evolutionary process in the interior of the ocean. We settled on a particular third order upstream algorithm that is both more accurate than lower order schemes and has the minimal necessary smoothing and dissipation as effective for turbulent flows and still being reasonably affordable. In 2001, the first open boundary conditions paper was written, necessary for a regional model, and its purpose is that it must let in the external influences that matter. For example, the basin scale gyrocirculations, and let internally generated radiative processes escape. This is something that is as much a matter of engineering art as it is a mathematically clean science, but nevertheless, it has effective engineering solutions. 2003 was a paper publishing the pressure gradient force in the distinctive coordinate system of ROMS, which follows the terrain and thus handles much better the topography of the ocean. This had been a bête noire of terrain following models beforehand, and so this was an advance in an accurate pressure gradient force. In the same year, we published our first regional equilibrium simulation for the California current, which is essentially the parent of all the ones that have followed. In 2005, we wrote the basic ROMS paper. At that point, you could say the core of the model had been published, focusing on the time stepping algorithm for the more rapidly evolving barotropic component of the flow and the more slowly evolving baroclinic. That is sort of tsunamis and thermocline fluctuations. It was also the year in which we had our first biogeochemical companion model. It was a rather simple NPZD, simple ecosystem model. 2006, publishing a paper on iterative grid nesting for final resolution. Next. 2007, a non-hydrodynamics alternative core for the, non-hydrostatic, for the workhorse hydrostatic approximation that is used in most ocean circulation models, actually most atmospheric general circulation models on large scales. And 2008 was the introduction of the biogeochemical element cycling modeling that Curtis will talk about. And it is a generalization of the ideas of NPZD, but with multiple plankton functional groups and multiple chemical cycles coupled together, and it sort of remains the current standard as at least a category of model in the global modeling community today. 2010 was surface gravity wave coupling, which matters in the surface layer of the ocean and near the coastline. 2011 was a particular treatment of the seawater equation of state to be accurate in the presence of the small but algorithmically dangerous compressibility of seawater. 2012 was a particular parameterization associated with the necessary small-scale diffusion processes that had the point of reducing spurious fluxes of materials across stably stratified density surfaces. 2014 was the first urban transport wastewater simulation. It was purely physical. It was a matter of releasing, passive material concentrations from the outfall pipes and seeing where they went. The simple answer is they went everywhere. 2015 was a change of the vertical advection algorithm to avoid excessive time step restrictions in very shallow water regions. 2016 was developing a parameterization for air-sea interaction where you really have to have adaptations of the surface wind and heat flux depending on the surface temperature and current conditions in the ocean. And 2021, which I think is certainly very relevant to this validation question, was when we published systematic California current system validations for ROMS and BECs in long papers in Progress in Oceanography. And the development continues. It's a living model, as certainly it should be, if only to keep scientific interest going. Next, this picture is just to essentially show the workhorse configuration that we used in the 2021 validation papers. You're seeing a map of SST on a particular hindcast simulation day. You're seeing the outer domain of a 4-kilometer grid. You're seeing a next level of a pair of 1-kilometer grids that overlap in the middle that span the whole West Coast closer to the coast. And you're seeing down near Point Conception a local subdomain, which might get down, which would have a grid of say 100 meters horizontally. And you would get to that from the 1-kilometer grid and with an intermediate step. We've made nested subdomains in various regions for various purposes. And these are one-way nestings in the sense that the parent calculation does not know about the child evolution under the premise that there essentially is a downscale control, that the dynamics locally are more influenced by the regional environment than they themselves influence the regional environment. This, of course, isn't perfect. It can be generalized, but it has served as a very useful paradigm going forward. Next. And the last thing I want to talk about is essentially how you go about assessing uncertainty. This is a problem shared, for example, with global climate models. You start with the plausibility of the model design. You certainly explore sensitivities of the answers to the way you've configured the model in domain and the various parameter sensitivities. You judge the solution behavior by its, physical plausibility and explainability. You make observational comparisons, recognizing, how limited the observations are and how much the observations and the model solutions themselves manifest intrinsic variability that makes, precise same time, same place comparisons more or less impossible. And finally, this is something in which modeling experience really provides a basis for judging the certainty or uncertainty of the model. And a very explicit way to do this, which the global climate modeling community has certainly adopted, is that you compare different models. Of course, their answers don't agree because there's an intrinsic irreducible imprecision in modeling as a consequence of all the design choices that different people make. But nevertheless, the intermodel comparison is, in some sense, the best indication one can make of model uncertainty, with, of course, the necessity to judge, how plausible and skillful the individual models are. I'll stop there. I mean, I put this slide up as eye candy. Why do we like ROMS? Why do we like a model of this type? Why are we interested in the turbulent ocean?
Thank you very much, Jim. So Kevin, if you want to come on and invite your panelists to start asking Jim some questions. Thanks, Jim.
Yeah, thank you, Dr. McWilliams, and I appreciate the admonishment on the title. I apologize for that. That was not well done by me. Thank you. Mr. Chair, questions from the panel?
Sure, thank you. Yeah, Jim, thank you very much for the overview of ROMS and the history as well. So I guess I have some couple of questions, but I would like to open the floor to the panelists first. Anybody has questions?
I see Neil's face. Neil, questions from you?
No, go for it, Gordon.
Sure. So Jim, you have the 3-layer nesting from 4 kilometers to 1 to 100 meters. Can you
That would be 4 layers.
Okay, so what layer or which layers the model are being used for this particular project?
If we're talking about the Southern California bight wastewater simulations, then it is in fact the one I didn't draw, which is the 300-meter grid in the Southern California bight.
Oh, okay. That's actually my second question. I was talking 1 kilometer to 100 meter. I was going to ask you about the 10-factor sort of jump in the
there's a step in between. We roughly
Okay.
make steps of 3 in grid refinement.
Okay, great. Thank you. Can you, and also so you mentioned it's one-way nesting, essentially a downscaling. Can you talk about, so I guess the 300-meter resolutions, so the influence from the larger scale model to the local process we're looking at is really the large scale processes. So the small scale process from the remote places. Can you talk about the influence of that to the, so say the sub-mesoscale process from the larger California coastal system into this particular area? Can you talk something about that? Maybe it's important or not important, or how to quantify that?
Sub-mesoscale dynamics are essentially local. And so the sub-mesoscale behavior outside the local domain is essentially irrelevant, except insofar as it might or might not be influencing the larger scale circulation. But the general experience is that remote influences in circulation are rather weak. There have been a variety of two-way modeling studies in the community over the years, and only rarely do they demonstrate an important, upscaling influence. The one exception is the tides. Remotely generated tides matter, and not in the generation of models that you're reviewing, but in the current generation, we actually have full gravitational self-loading forcing of the tides in the Pacific Basin, and that does make a difference to tidal behavior in the Southern California Bight. On the other hand, I don't think it makes a very important difference to the fate and transport of the local pollutants in the region compared to the locally generated tide contribution.
Got it. Thank you. So that's the question I have so far. Any other questions from the panel?
This is Faye.
Hi, Faye.
Hi, thank you, Jim, for this overview, the history of the ROMS development. So I have two kind of questions. One is really how this model responds to different climate forcings and extreme events, synoptical events, such as the marine heat waves or the ENSO, the dynamics. This is really how you handle this in a way through the boundary or atmospheric forcing. This is kind of one question. The second one, so far I understand this model is a free run model without the data simulation. So when you get into the real time simulations in the more like operational sense, what is your view for using the data simulation to constrain the model as close to reality as possible? So those are basically two general questions.
Let me take the first question of, let's say, climate variability. That is, of course, partly expressed through the local forcing, which in itself, is subject to climate variability, things like, ENSO along the coast. And through the open boundary conditions, that is, you have to have external data, whether a basin scale simulation or some sort of an operational product, like, for example, the Mercator product from France, which now has a different name, I forget. And, we've written papers on climate variability, including global warming change papers. I certainly don't see any intrinsic limitation to model handling that. As far as, extreme events, if it's a big storm, then that's local. And so that's within the domain, as long as you have the meteorological forcing data to reflect it. Sorry, I'm blanking. Your second question, prompt my memory.
It's really the data simulation.
The data simulation, yes.
Yeah.
We have I would call it a continuing small project with Zhijin Li, who used to be at JPL, is now at Fudan University in China. And I think he has as skillful data simulation techniques as anyone in the world. And he currently is working with us on some Pacific and California current assimilation cases. I have a bad reputation in the community as being an opponent and scoffer of data simulation, which is only partly true. The real issue is, if you want to know what's happening today or yesterday, then of course you have to assimilate data, because the ocean is a chaotic system, and the models yesterday is not going to be the same as real yesterday. On the other hand, data simulation is an inherent compromise between the constraints of the observations, which are from one realization of the universe, and the evolution of the model, which has its own dynamical integrity and its own realization of the universe. And, a compromise is an uncomfortable thing, and you basically damage the data and damage the model when you do it. But if you have to do it to forecast the weather, then go ahead. You want to argue about that?
Thank you. No. I visited Jin and Lee in Shanghai a few months ago. We had a long discussion, and he showed me some of the products. I'm superly impressed, and especially on the very, very fine small scale. We're working together actually through some projects here in China. Thank you for that answer.
All right. Any other questions? Alex, do you have any questions?
Jim, it's honor. See it and
Hi,
hear
Alex.
you talk. I totally agree with you on data simulation, right? And I've done probably more than some other people. So it depends on your task, and I do agree with you. So maybe if I phrase it as a question, so and that's question from the last meeting and this meeting. So am I to understand that the main goal for this development is to provide scenarios rather than kind of give you the forecast for tomorrow on a consistent basis?
Yes, we are trying to provide a virtual reality that will pass fair Turing tests.
Yeah, that's great. That's the same thing as we do. Like we provide products for people who want a newspaper or who wants to know something for tomorrow. And like you say, if you simulate some, you correct something, since you don't have good data everywhere, you silly kind of hurt somewhere probably. So it's too bad that in this competitive science environment, people actually stop showing those results we used to. But there are hidden skeletons sometimes, and including what I'm doing for now. And we also, for people who are interested to know in scenarios and look at basic effects, we also provide like high resolution, non-DA solutions like you do here. So it's totally consistent with our practice, at least. So right. So and I do hope that we'll still, since this model is forced by Mercator apparently, right, which does know about El Nino, right? So I'll be curious to see maybe somewhere along the way kind of statistics that show how we do, like in a 14-16 El Nino or this El Nino that's coming, right? Like in terms of phenomenology, it's not just sea surface height rise, it's slope flows, it's shelf anomalies, it's undercurrent anomaly. People have been working on it. Some of the recent results show like if you don't provide that as boundary conditions, and I think that's the south boundary conditions mostly, right?
Yes.
Then your variability in sea surface height is much lower than observed, right? So the south boundary doesn't matter here. And even and you may provide the boundary conditions there, but depending on how you actually implement the boundary conditions, you may get desirable result or better or not so good. So I'll be curious to see those anomalies if you guys have like long run and like basically anomalies from the seasonal cycle during extreme events. So that'll be interesting.
That would be fun to do.
Yeah, and especially like when you go from the 4 kilometer to 1 kilometer. So basically you have this cascade. Does this information propagate actually?
Yes, it does.
Cute. Yeah.
Mr. Chair, we still have plenty of time for questions. So
I
other
still have
panelists?
some questions. If I don't know, but I want to give the opportunity to other people on the panel as well. Mike and Margie and Neil just raised his hand. Go ahead, Neil.
Yeah, thanks, Jim. I was wondering if you could remind us how terrestrial freshwater input works on all the different levels of the nested models down to the 300-meter Southern California one, because I got the sense from my reading that it changes at a certain point, or maybe it doesn't.
It does, because essentially at the coarsest resolution, you can't begin to resolve the river plumes. And so you basically just have to have a correct total mass source in the general vicinity of the river, which of course comes from some sort of a terrestrial runoff data set. But as you go down to finer resolutions, then you can begin to actually open the river mouth to the actual flow. Just to pick some examples, we've done some Mississippi River simulations, down in the order of 100 meters, and we go up about 20 kilometers from the mouth of the Mississippi to set the boundary conditions. And we do something similar when we're doing San Francisco Bay. We go up the Sacramento River a certain distance to set the boundary conditions. But you can only do that when you have the resolution comparable at least to the scale of the river plume, if not the width of the river itself.
So in the finest 300 meter SEB grid, there are explicit freshwater point sources. I mean, point sources
Yes,
in the,
yes.
yeah.
This is a
Okay.
data set that SQUIRP developed essentially of, anthropogenic pollution sources and terrestrial water sources, and, even rough depictions of the atmospheric deposition sources in a geographically detailed way.
But
And
the next nest out from that, it still has a sort of a mass balance approach out to,
somewhere in there, we
I'm-
make the transition. I forget exactly where.
okay. Okay, thanks.
Yep.
Thank you, Neil. Mike or Margie now?
So I'm not a physical oceanographer, so I'm far more on the biology and biogeochemistry side. But I was wondering, as you get to the higher resolution models, like the 100 meter and 300 meter resolutions, how are you validating those? Because that gets at higher resolution than a lot of the satellite outputs are and a lot of our field sampling is.
You basically have to go back to the last previous slide, which although can you do that, Martha?
Yes. Hold on one second, Jim. Let me get there.
I mean, this is called uncertainty assessment, but it basically could be called validation. And, it's a mixture of these judgments. I, personally put a lot of weight on number 3 and number 5. But there's a certain amount of hubris in that statement. Feel free to argue with the outcomes. But I mean, it's a real problem. I mean, there is no observing system that can keep up with what the models can produce.
Yeah. Okay, fair enough.
All right, Margie, I know you're in the car. I don't know whether you want to ask any questions. If let me see where
Alex does.
No, nothing else for me. Thanks.
Okay, Alex has an. Go ahead, Alex, please.
Yeah, I was actually trying to go against the current here and look at number 2 and number 4 in that list of papers you guys supplied to us to read about skill assessment. And every time, kind of, maybe I don't click on the right link there, but most papers that were provided give us talk about even about climate, but really we don't see those basic model data comparisons. It's still a operational model in some sense, right? Even though it kind of provides scenarios, it would be actually
Yes, but
I don't think that just like modeling experience and solution behavior plausibility. How do you assess plausibility? That's kind of if you resolve turbulence to 100 meter scale. So it would be probably you guys looked at a spectra, right? Or maybe you didn't, right?
you
Stuff
look at
like that. So
everything.
we need to compare to the data, and I think we compared to like 1999 when it was when I started on the West Coast, when we really were looking for data. Now we have more data that we can handle. Still, it's still not enough to maybe constrain the solution, but we have a lot of data that we have to process in a creative way to compare to the model. Sometimes statistically, sometimes going to looking at RMS correlations and stuff, right?
Well, I agree. Number 4, observational comparisons, I think we have certainly written papers on. The ones I mentioned were the whole coast papers, and I think that, you know, Curtis is going to be talking, well, I don't know what Curtis will say, but, you know, in the list of papers, there certainly have been a number of Southern California bite, you know, validation, comparison to observation papers. They were probably presented in the last seminars in December. The correct configuration and parameter sensitivities are typically something we don't publish because, you know, they're tedious and they tend to be kind of random walks through possibilities. But it certainly is something that, you know, has to be done, and, you know, we all do, and I'm sure you do too.
Yeah, it's not a criticism, it's just maybe a statement request to our leaders here to maybe kind of resend at least to us, or to me at least, because the one that was the couple of links that were supplied in December, maybe I was looking in the wrong place. I clicked on those. I didn't find much in terms of really
Well,
model comparison.
I'm
At
sure
the cost scale, at least.
Martha can give you more links, I'm sure.
Yeah. All right.
So Alex, after the, today, I'll just make sure, again, you guys, you know, I provided a reading list. You know, I think that Dr. Zhang wanted to manage the fire hose. So I'm not exactly sure how was that managed in terms of what, you know, he sent over to you guys, but we have a full list of modeling science publications. So we're happy to send that again.
Yeah, and that's why I kind of tried to find what I was looking for and I couldn't. But maybe it was, maybe I was not looking in the right place. But if you can resend that, that would be nice.
Okay, great.
Yeah, there is a longer version of the reading list, Alex. I'll make sure you have a copy of that. So we still have 1 more minute. Just one quick question, Jim, for you. I think that's related to what you just been discussed about observational comparison. So I know you guys have done the extensive model validation comparing to observations for these models. That's great. But those are done in the past. But I assume the model validation is a continuous process, right? So it's going to, you know, this model is going to still be here and for future use, or in terms of guiding the, you know, the decisions on the wastewater release of it. So what about what's your thought on the future validity of the model? The ocean environment is changing. So you think fundamentally, once we validate the model for the past period, the model should be good for the future as well? Or is there something we should watch out for?
Well, that's a trick question, isn't it? I think the most interesting thing that comes to mind by your question is we're in some stage of transition from this kind of model being a research model to it becoming a kind of operational model for, in particular, the management community, which means that it needs to be, you know, a continuing process. There needs to be a labor force that will do that. And, you know, I'm probably not the guy who's gonna, you know, do this year's river flow out of the San Joaquin Valley. And of course, there need to be continuing observational programs. I think the IU's programs do a pretty good job on the larger scales. The BITE program of SCUS does a pretty good job in Southern California BITE on the shelf. We're sort of missing observing programs, you know, on small scales near, for example, San Francisco. But the same way that, you know, the weather community has built out its operational, observational, and modeling capabilities, I think the management community needs to do so, and that's going to have to be management money, not NSF money. And, you know, if you guys wanted to recommend that management step up and, you know, invest in their future, then please do so.
Great, thank you, Jim. So Kevin, you're back to you. Alex, I
Indeed.
think we're running out of time. I think we should move on.
Yeah, exactly. It is time to move on. I appreciate that was an excellent conversation. Thank you all so much. Now we're going to move into the biogeochemical elemental cycling model development, setup, and validation. So Martha, I'll swing it back to you to introduce Dr. Deutsch.
Okay, well, so Dr. Deutsch got his introduction, so just to maximize discussion time, take it away, Dr. Deutsch. Thank you,
Thanks.
Jim. That was great. I appreciate it.
All right. Welcome, everyone. Can everyone see my slides? Moving into the
Just as like a slide view, can you, there you go.
There it is. Thank you.
Okay, great. Well, I'm going to pick up right where Jim left off and give an overview of what's downstream of the physics in the ROMS modeling system. In particular, to focus on the biogeochemical and elemental cycling model. And I want to sort of do two things in this presentation. One is to give folks who are not familiar with it a kind of overview of the basic ideas that go into the model construction. What's its foundation? How is it formulated? How do we parameterize processes that are central to how biogeochemical cycling works? How do we approach evaluation of sensitivity to unknown parameterizations or parameter values themselves, and then also to the boundary conditions, which, as Jim already mentioned, is a fairly important feature of a model at this scale. And then the second part of this talk is really going to focus on what you all were just asking about, namely the empirical validation of model solutions. And for this, I'll be focusing on the kind of what I'm going to call climate scale grid, which is that outer 4-kilometer grid in which one can see certainly interannual and bordering on decadal or at least multi-annual variability, things like ENSO. And I'll focus on the data sets we use for that validation that cover a variety of timescales from seasonal out to multi-annual. The relationships that we see in that variability as a way of evaluating whether the model is doing the right variability for the right reasons, namely that these relationships between properties tell us about the underlying mechanisms that drive variability. Okay, and I'm going to be presenting this on behalf of really a larger team. I think you've met most of them through past webinars, and you'll meet more in the future. So here are just some kind of eye candy animations to give you a feel for the dynamic nature of this region, the California current system, from some of the model simulations that I'll be showing you. Of course, it starts with the physical realization of the system, and Jim already presented, the structure of that, how it's based on the fundamental equations of stratified fluid flow on a rotating sphere. And the idea of resolution trade-offs are intrinsic to the choice of these model domains. So I'm going to focus on the one that you're seeing here is the same one that Jim showed, the 4-kilometer outer nest, which is good for establishing large-scale patterns. You get a very large dynamic range. You can, and yet we're at a resolution where we can simulate conditions over many years and even decades, so that we can look at things like decadal scale trends and climate variability in the past and future. The ecosystem model in the middle column here is just the animation of surface chlorophyll. We'll look at that more in a minute, but it essentially describes in very simplified terms the interactions between phytoplankton that perform photosynthesis and the zooplankton that graze on them, and the net effect that they both have on the generation of detritus and other organic compounds that circulate through the ocean and generate respiratory demand, low oxygen zones, low pH, and so forth. That ecosystem models we'll see in a moment has multiple kind of nutrient elements and phytoplankton functional types or characteristic species types, if you like. And then the third component is sort of closely related to the ecosystem representation, but it's getting toward more of the chemical effect of all of those ecological interactions. So we refer to that as biogeochemistries. Interested in the questions like, what is the fate of organic matter? How do particles, once they're formed, settle out of the sunlit surface zone? How does dissolved organic matter get transported by the flows? How do the nutrients like nitrogen and iron that have inputs exogenous to the ocean, either from the sediments or rivers or the atmosphere, influence the ecosystem properties? And then finally, of course, the carbon and oxygen cycling that are induced by those biogeochemical cycles, or a facet of those cycles, including particularly hypoxia and ocean acidification. So the foundation of the model is a fairly simple principle. It's just the conservation of mass. And so at some level, when you're in the ecosystem and chemical realms of ROMS, you're really just trying to do a very complex technical bookkeeping of all of the different forms and transports of a given element. So that might be carbon, it might be nitrogen, it might be oxygen, or all of the above and many more. And the rate of change of the concentration of any of those elements is the difference between what flows in and out by physical processes. So this is advection that Jim referred to, the flows carrying nutrients or carbon or any other element in or out of a given grid cell of the model. You have mixing, typically meant to represent unresolved flows. Of course, as you get down to the smaller scales, there's less and less of the flow that is unresolved. And so this changes depending on your model resolution. And then the thing that I'll be focused mostly on here in the biogeochemistry are these representations of biologically or chemically induced transformations of elements. So I'll use T to represent the biogeochemical rates of transformation that can operate on any of those elemental constituents of seawater, and also involve a fairly large number of parameters to translate essentially how much chemical there is into a rate of transformation in or out of that particular reservoir. And then, of course, in the chemical realm, we also have external forcing. So that would be, for example, your riverine inputs of nutrient or anthropogenic nutrient inputs would also be CO2 invading the ocean from the atmosphere. Anything that's sort of external to the ocean, but coming into it would be in that external forcing term. In the interest of time, I think I've basically said everything that's down here. Your state variables, your parameterizations and parameters, the rates of transformation, which we'll look at in some depth, and then the forcing, which we'll just touch on very briefly. So as Jim mentioned, the workhorse model for much of the ROMS studies that have been undertaken in this group over the past decade or so have been a particular version of a multi-component surface ecosystem model called BEC. So it's the biogeochemistry and elemental cycling model. It's on a biological level, it consists of a few different functional types of phytoplankton. So one of those functions the differentiation of phytoplankton types is based on size. So you have small phytoplankton and large phytoplankton, diatoms. You have calcifying plankton and coccolithophores, or parameterized according to coccolithophores. And then we have nitrogen fixing plankton, which are not so relevant for the California current. And that reminds me that, the whole structure of this model is inherited from models that were developed to simulate global biogeochemical cycles. And when this was implemented in ROMS for the first time, it just adopted the same parameterizations and parameter values as the global model. We've done some tweaking to that, some additions of new processes, but by and large, the basic functional forms of the transformations are all what they have been in models of this categorical type for several decades now. So the biological components here, the phytoplankton and then the zooplankton that graze on them, ultimately are extracting dissolved constituents from seawater in the form of nutrients, which we represent through 3 different nitrogen pools, iron, silicate, and phosphate, all of which are able in principle to limit the rate of phytoplankton growth. Those elements get returned through excretion and respiration by the combination of phytoplankton and zooplankton. The CO2 and the oxygen that gets exchanged through the photosynthesis and respiration induces an air-sea exchange. Sorry, my cursor is in a bad habit of disappearing. It's gonna, so, oop. I like to be able to point to things. Laser pointer, here we go. So we have air-sea exchange of the gaseous components of biologically active elements. Some forms of atmospheric input and terrestrial input on the nutrient side, primarily for nitrogen and iron. And then finally, we have the pools that represent biologically active elements, but that are in a kind of dead phase. So detritus, either too small to be to settle out gravitationally in what's called dissolved organic matter, or in larger particulate organic matter that can sink through the water column. Those get formed by the processes represented in the food web, and they get remineralized through an implicit but not explicitly represented bacterial process of respiration and remineralization to complete the cycle by reintroducing CO2 and the nutrients and consuming oxygen. Okay, so these are a lot of processes, a lot of transformations happening, and each one of them must be represented in a simple mathematical formulation. It would be way too much to go through all of that. But what I want to just do is sort of highlight the categories of these and the number of parameters that are involved in realizing each one of these representations. So we've got compartments labeled here on the left, from phytoplankton, zooplankton, then particulate detritus and bacteria, although bacteria again is not explicitly represented, and then chemical processes here in the compartments, each influenced by a variety of processes, and each one of those processes has a number of parameters that is required to specify the full relationship between the abundance of an element and its rate of transformation. And then over here on the right, I'm giving you a very crude, my own kind of crude subjective take on how well these various parameters are constrained by external information, information that one can glean from laboratory experiments, sometimes field studies. How well do we know either the functional form and or the value of parameters that go into these? And roughly speaking, the closer you get to the base of the food chain, the better understood these parameterizations are. And the further away you get, the more uncertainty there is in both the functional form and the parameter values. So if you just want to focus on one thing, I'd say focus on the bottom line, which is that there are something like 90 different parameters needed to specify all of the inner exchanges between the different elements and their different forms between inorganic and organic reservoirs. And that is way too many to do any kind of fully systematic exploration of the parameter space of the model. So one has to do that in a more subjective, some might say ad hoc fashion, but guided by our understanding of which parameters matter most to any given target variable. And we've done a fair amount of that. I'll show you a little bit of it later on. But first, I just want to comment on what I think would be one of the primary parameterizations that would interest this group, which is the relationship between phytoplankton growth, which is of course associated with the photosynthetic drawdown of CO2 and production of oxygen, and the nutrients that are available for fueling that growth. And this is a very well-known, these curves represent very well-known relationships that one can derive from enzymatic kinetics and observe fairly directly in laboratory studies. So this is on the high end of our confidence in a proper representation. Doesn't mean it's perfect, but it's at least got a lot of empirical support and theoretical support. And what I'm showing here are the curves that are in the model to characterize both the large phytoplankton and small phytoplankton, very characteristic response that at low nutrients, an increase in nutrient results in a very large response in growth rate. And as you get toward higher nutrient levels, those responses tend to saturate. They saturate more quickly for small phytoplankton, as shown here, and more slowly for large phytoplankton. So where you are, this just is illustrative of the nonlinearity in many of these parameter formulations. That is that the sensitivity of a model solution to changes in, for example, the nutrient concentration at which you reach half the maximum height of this curve is going to depend on the baseline state. So it not only depends on what your nutrient parameters are, but it depends on the state in which you're perturbing those parameters. So it becomes a very difficult thing to constrain the full state parameter space sensitivity when the formulations are as nonlinear as this. There's another important reason for showing that, which is to compare it to what the Southern California current looks like in terms of the nutrient concentrations on the same scale. This is a log 10 number of observations from Cal Coffee, just showing you that by far the surface ocean, and in fact throughout the photic zone, the most commonly observed nutrient levels are at the very low end of the scale, in which both large and small phytoplankton are in their more sensitive limit, which is to say that for most of the California current, particularly in the south, the response to small variations in nutrients can be substantial. So we, in the process of sort of further developing this BEC model for use in the ROMS physical infrastructure, we pursued a whole variety of sensitivity studies that were essentially just taking the existing parameter values, doubling them, halving them one at a time, to look for parameter values that could be need substantial tuning to be functional in the California current, because that current is suddenly much better resolved than it was in the global community Earth system model out of NCAR, from which the BEC model derives. In a nutshell, what we found was that most parameters will have some influence on a target variable, for example, net primary productivity. The influence of any given parameter on net primary productivity is also going to depend on where you look. The magnitude of its influence on net primary productivity will depend on what the parameter is. Typically, something closer to representing phytoplankton growth is going to have a larger impact than something a bit further away from the fundamental representation of phytoplankton growth. So here I'm showing you just an example of a sensitivity study that was conducted with by manipulating the quadratic dependence of zooplankton mortality on the amount of zooplankton itself. So this is a kind of common and one might say even inescapable representation of an ecosystem closure. That is, how do you prevent the top of the food chain from what do you do about the losses from the top of the resolved food chain? And in this case, the top of the resolved food chain is zooplankton. There are no fish in the model. And so this quadratic mortality is that ecosystem closure, and this just shows you that cutting the quadratic mortality coefficient in half has a noticeable effect on the net primary productivity. It is not a massive effect if you just look at the difference here, divide by, I mean, you can see that there's a difference between the base case here in the middle and then the halving of the quadratic mortality for zooplankton. The difference here is a relatively small fraction, around 5% of the base case. So this is not going to be, although it's one of the main uncertain parameters in the model, it also has a relatively modest impact on the solution, to the degree that your solution is the property of interest is this net production of organic matter. In contrast to many of the ecological parameters, we found that there was a much stronger sensitivity of model solutions to the choice of boundary conditions. And so a substantial amount of work went into choosing boundary conditions that had fidelity to the observations. And Jim already mentioned the Mercator, the hindcast basin scale simulations by Mercator were what we ended up settling on as giving the most realistic representation of the Eastern Pacific hydrography, and they perform very well as forcing for the open conditions within the ROMS system. So, and that's true at a physical scale. It's also true at a biogeochemical scale. For biogeochemical conditions, we had to rely on a variety of different sources of information because things like iron are relatively scarcely measured and certainly not simulated in most basin scale hindcast simulations like Mercator. So we constructed boundary conditions from a variety of sources and ultimately tested them by validating against observable properties of the ocean. Let's see, the other boundary condition that you may be interested in are the biogeochemical fluxes at the ocean boundaries. Here are the benthic fluxes associated with iron efflux, especially prominent under low oxygen conditions, and then also the nitrogen influx into the sediments, which is also associated with low oxygen conditions. These are sort of both forcing, but also part of the model solution in the sense that we used empirical observations to create new parameterizations for these based on bottom water conditions. Okay, so the empirical validation is focused on three properties: mean state, natural variability, and property relationships. Can someone give me a time limit, Martha? You look like
actually, Curtis, so I think what's probably useful, since the panelists have all your slides, is to just give a high level sort of punchline on the validation. Okay. And they've got your slides, and so that's a great jumping off point for questions.
Great. Okay. High level is that we validated the model as best we could using all available observations. And that includes satellite remote sensing, altimetry, scatterometry, and chlorophyll, hydrographic observations from the historical World Ocean Database to capture both seasonal cycle and interannual variability. And then for many of the biological variables, Cal Coffee, which has a much more in-depth suite of observations on ecological things. The chlorophyll mean state is reasonably well represented. So is the seasonal cycle in terms of its spatial pattern of variability and the seasonal phasing and magnitude of that variability. Net primary productivity we could evaluate through both satellite reconstructions and also Cal Coffee direct observations, bottle incubations, also well within the uncertainty in that those biological rates, which are substantially uncertain at an empirical level. We can evaluate the trade-off between nutrient and light limitation by looking at the depth of the deep chlorophyll maximum and the biomass peak associated with it, although not always at the same exact depth. The trade-off between nutrient and iron limitation. So there is iron limitation in the California current. It's been observed. We capture the overall magnitude of that relative iron versus nitrogen limitation as it's been observed in the Central California current system. The tracer variability and mean state for nutrients like nitrate is also well simulated in this sort of climate scale. The variability we can attribute to the strong role of shifting pycnocline, partly driven by winds in the forcing data sets. That ultimately drives a lot of what the net primary productivity variability shows in a way that's pretty consistent with what people have observed in historical observations from Cal Coffee. The net primary productivity leads to an export of organic matter that is within the range of what people have observed in empirically based models for the ratio of export to NPP. The vertical structure of cross sections through the coffee from Cal Coffee also it has a reasonably well reproduced by the ROMS simulations, both for nitrate and oxygen. The spatial pattern of oxygen variability from World Ocean database is also well captured, as is its variability over time, which again derives to a large degree from pycnocline heaving, as well as water mass mixing ratios along isopycnal surfaces as seen in salinity or spiciness. The carbon dioxide fluxes from the atmosphere are also well simulated, although with a very much more scattered database. And then finally, the aragonite saturation state, as you would guess from oxygen, is fairly well captured in terms of its overall structure. And then last slide, in the long-term trends, oxygen declining over the period of interest, along with the saturation state of aragonite. You can see the trend here. We don't know it from observations, but the model passes through the data that was available from this simulation period. Oxygen, we have much more observational constraints on from Cal Coffee. Folks were asking about ENSO. Here's one the famous 97, 98 ENSO here, which shows a kind of depression of the pycnocline, and that's associated with a temporary elevation of oxygen within this density class that is well represented by the model. We haven't done exhaustive surveys of other ENSO events, but here's one that's very large and very clear in the observations. And that sets us up to do things that you'll hear more about in the next presentation, by like looking for ecosystem responses. The model is very instrumental to being able to fill in a lot of information about what has driven historical changes in species population abundance. And that northern anchovy was our first foray into that using this modeling system, and it really helped us to make pretty reliable predictions about what the fluctuating abundances and habitat structure was for northern anchovy. And I think you'll hear more about that from Christina next. So with that, I'll just summarize by saying that the model hindcasts do a good job, to the degree we have data to constrain it, of reproducing historical variability in the California climate current system, and the relationships between those components of variability that are indicative of the underlying mechanistic drivers of that variability. And I think I would make the argument that these simulations provide a reliable baseline for further downscaling, for evaluating anthropogenic inputs, and also for species and ecosystem responses. And I think you'll be hearing more about each of those three things from Faisal next webinar and from Christina in the very next talk. So with that, I'll be happy to take your questions.
Great. Thanks, Curtis. Kevin, take it away.
Yeah, Curtis, thank you very much. I know that's tough to digest that all down into such a small time. Thank you for that effort. Mr. Chair, any questions from yourself or the members of the panel?
Oh, sure. Thank you. Yeah. So since we have a few experts on biogeochemical modelings on the panel, maybe we should start with them first. Faye, Margie.
I'll just let people shout out, but Neil has his hand raised, so please.
Oh, Neil too. Forgot. I haven't seen that.
Yeah,
go ahead,
thanks,
Neil.
Chris. That was great. And yeah, I mean, but before I ask a couple of slightly annoying questions, I just want to say that I think the validation effort you've done on this model is really impressive. And I especially like that you focus on relationships between variables and not just point-by-point values, because there's so much more information there. But I wanted to ask you about or the parameter exploration that you summarized as only leading to like 10% changes in NPP. So first of all, it seems to me like 10%, I mean, that's very small, really, and sort of shows that there's, I mean, my interpretation is there's something sort of inevitable about the level of NPP in your domain, you know, in that averaging box being what it is, which I guess has to do with basically how much of the limiting nutrient is brought up into the light. But I think 10% is smaller than the data model disagreement that you also showed. Do you think I'm interpreting that right? And what do you think that means?
Let's see. The data model disagreement, when you, I guess you would be thinking of
like with the satellite,
something like this.
Yeah, let's say that, for example.
Yeah, okay. So here I need to move my the black line represents ROMs, and red and blue represent two different satellite products that are purport to estimate NPP. And I'm sorry, I can't remember which is which. And I didn't label it. So you're right that, you know, if you believed in one particular satellite estimate, the model would not, on a seasonal basis, always be within 10%. And that, in that sense, you know, whether the parameter sensitivity could improve on the model at that level is unclear. I mean, one thing we didn't do was try to combine different model parameter sensitivities to really optimize. I mean, and I should say that, you know, of the 90 parameters, we probably did 20 individual parameters. We didn't do simulations for all 90. We chose 20 that seemed like they would, you know, have the best chance of changing productivity. For example, you know, we knew that like a large fraction of NPP was driven by large plankton and not small plankton. So we didn't bother changing the half saturation of nutrients for small plankton. Things like that. We just made subjective judgments, and then we did not try to, you know, combine, well, what if you change multiple parameters at a time? And we didn't also try to, like, in any way kind of within 20 simulations and 90 parameters, you can't really make a sort of optimal solution. So what we really did was just try to find areas where the global parameter sets, which, you know, were tuned to global NPP and other things, had a very systematic bias, and then we just tweaked those to achieve what was a sort of, as Jim said, random walk through this parameter space to result in a simulation that was as close to within uncertainties in the observations as possible. So just to clarify our process. But to answer your question, I mean, I think, you know, if one were to do many more of those simulations and really have a clear objective function, you know, you could certainly do better at a regional scale. You know, I'm not sure, like, whether you'd have a Pareto improvement in the sense of, you know, things get better in all seasons and in all parts of the California current seems very unlikely to me. And it's also unclear whether NPP, you know, one can, depending on your emphasis, right, you might be trying to optimize parameters to reach NPP. You might be trying to, you know, optimize towards some other variable. So we were just trying to be, we took a sort of a good enough approach, given that we couldn't possibly truly optimize. We just looked for opportunities to improve in a kind of clear fashion. And
Yeah,
then
I mean, there's
go ahead.
optimizing, and then there's exploring uncertainty. And really, I think, I mean, I assume this is a topic we're going to come back to next week, maybe in the context of the SCB in particular. And other hands are up, but I just wanted to make one other comment, you know, about this question of what variable you organize that sensitivity around. It did look to me on your example of the changes that mortality makes, that although the total NPP is probably, I mean, is obviously quite similar, there's quite a difference in the spatial scale. Like, you know, in an advective system, the spatial scale offshore and the time scale are indicators of each other. And it looks to me like, you know, there probably is a lot of uncertainty in, you know, how long it takes the system to digest that new bit of nutrients, you know, send it through, which is probably extremely relevant to how much hypoxia and acidification you get out of a given bit of phytoplankton growth.
I mean, so you that's an interesting point, and it leads me to another response, which is that when we did these sensitivity experiments, we were really just looking at, we really just ran them for, I think, 2 years. So we would tweak the parameter, run it for 2 years, just look at the last of those 2 years and look at plots like the ones you're looking at here. What we didn't do was look at response to perturbation. So you could, for example, imagine that a lower quadratic mortality, just to use the example, to recycle that example, could be more important to the response to an interannual wind change than it is to just the mean NPP. I think that's kind of one of the things you're highlighting, and I certainly agree that looking at things like response timescales to physical perturbations would be another way of going about evaluating the importance of parameter uncertainty.
All right, thank you both. I think we're running out of time, but I think at least we should. Mike, do you go ahead? I think we should. It's okay for us to encroach into our break time a little bit.
Thank you.
Okay, Curtis, I really liked your talk and your general approach, and I was kind of curious. Mostly you talked about either vertically integrated things or surface validations. And I was wondering if you've really looked much at the dynamics of the deep chlorophyll maximum in the model. And I ask that for a few reasons. One is that obviously it's something that's a little bit harder to do because we don't have remote observations of the deep chlorophyll maximum, but also the deep chlorophyll maximum kind of mediates the exchange of deep nutrients up into the euphotic zone. And it's also been a region that some recent results have suggested that there may be pervasive iron limitation at the deep chlorophyll maximum in the region. So I was curious if you've really kind of looked at how the model's behaving at the deep chlorophyll max.
I think the best answer I can give you is to go a little bit deeper into this figure. I don't know if it's going to answer what you're really after. I mean, probably the real one-word answer is no. We haven't really looked closely at the dynamics of productivity or biomass or tracers within the deep chlorophyll maximum itself. We primarily used it as a measure of whether we sort of adopted a fairly common assumption, which is that it reflects the kind of nutrient light trade-off. And in the model, it certainly does. And then just, computed the depth of the DCM in observations and the model. And in the model, it well reflects there's slight differences because of photoacclimation, as you know, between the depth of the chlorophyll maximum and the depth of biomass maximum. But they're relatively minor in the region that we have observations for. And that depth in both of those was well captured by the kind of depth at which the product of the light and nutrient limitation reached its maximum, which is to say that in the model, the reason why at least the biomass reaches its peak at this depth is because that's where growth rates reach their peak. So there's a kind of local, the advection doesn't seem to be playing a large role in what sets the depth of that maximum. That would be a starting point for, exploring your question in more depth. But that's on at least an annual scale. That's sort of my impression of what we got from this analysis.
Right. Thank you.
Thanks.
You might have okay.
Margie, you
Looked like you might follow up there, but
yeah, we can continue this discussion. Mike, yeah, we'll take a note and then we can continue this next week in person. Margie, go ahead, please.
Yeah, hi. Yeah, it's a great presentation. Yeah, and I just, Faye and I worked with Keith on optimization of this model and compared to the others. Anyway, it's so boy, that was like 20 years ago now. So going back so anyway, I fully appreciate the difficulties in doing such parameter optimization. So anyway, I wanted to I feel like I've been there, done that, worked on parameter optimization so much. I wanted to kind of take a different, think of this in a little different way. And I kind of was thinking about, of course, I come from the Chesapeake Bay on the East Coast, so a very different system. But I guess I'm curious about how taking this open ocean model, and it was, just like you mentioned, I was already going to ask you about it, but you said this right off the bat, that this is an open ocean model that you're adjusting to the coast. And so, either, maybe now you can say a little something, or next week we can talk about this more about some of the changes you've made. And so you mentioned some additions, and I was wondering if there'd been any subtractions also, like things that you don't like I was wondering, is iron really important? But you showed it was a little bit. So and then you didn't show silicate. So I was curious, maybe silicate is just, did you turn silicate off? And I'll ask a lot of questions and you can choose which ones to answer.
Sure.
Diazotrophs, are those off because I wouldn't think they would have a big role, and there might be some benefit to just turning it off rather than having an unimportant thing with unknown parameters that could cause huge errors. If it's not that important, it's probably best just to turn it off. Another interesting thing I thought of difference between what we do on the East Coast or Chesapeake region is in the coastal region is ammonium is really important. And so you talked about you have this nitrogen pool, but then you based it on nitrate observations. And of course, nitrate is not nitrogen because you got the ammonium in there too. And so I was curious if you ever thought about ammonium, or if ammonium, from the sediments, I would think that would be important and the very close to the coast. And then, and then inorganic sediments. I mean, I know you don't have the large rivers that we do, but there's some rivers, and does sediment not block any light? That's really important for us in terms of light limitation. And I guess just whether you have, so this is a much more complex model than I'm used to looking at. And, do you really have, is it beneficial to add some of this complexity when we don't necessarily have all the observations, or is it better to have a simple model that can be more well constrained? If there's a part that's unconstrained, should we just turn it off? Like iron from the sediment, I think that was like bottom, maybe we could just turn it off. Anyway, so that was a whole lot there, some various different questions, and maybe we can talk about it more later, but those are just some of the thoughts that were going through my head.
Great. There's a lot there.
Curtis, I'm sorry. I hate to interrupt you, but it's really important. We got to keep moving here.
Yep.
And I think that what Margie's done is laid out a really good kind of outline for a part of maybe our conversations next week. So thank you. I want to get to Faye,
Sure.
Gordon, before we take our break, if we can get that, and maybe we'll get a quick answer, or maybe we have to park it for next week. But Faye, please ask your question so that we can get it on the record, and then we'll figure out how to approach the answer.
My question is very simple, is that you focusing on 4-kilometer West Coast solutions. Has anyone or your group or other groups, people look at a geochemical solutions with the different level of the physical configurations? You're down to 1 kilometer, you're down to 100 meters. I think this is really important, is how the biogeochemistry ecosystem behave in response to the different physical settings. And that's the overall. The other one, I think, you don't need to answer it. Maybe we can discuss this. When you get down to the very, very coastal 100 meters resolution with a different anthropogenic inputs, for this purpose, the wastewater treatment discharge, I think the nitrogen dynamics, especially the ammonia and the nitrate, that interaction need to be looked at very carefully. Now all the nitrogen created E. coli.
Thank you.
Good, thanks, Faye. I appreciate you getting that on record and being patient with that being part of next week's presentation. So, Gordon, any other questions before we take a quick break, and hopefully we can get right back to work here after just a few minutes? Any other questions?
Not really on my side, but I think, yeah, so it would be great. Next week when we meet in person, we can continue this discussion. There's a lot of good questions here. Thank you all, Neil, Margie, Faye, and Mike.
Yeah, this was definitely our best Q&A session. So I appreciate the presentations this morning from Dr. McWilliams and Dr. Deutsch. Martha, thank you for helping keep us on track. We did pretty good. Let's take a break here now. I know it's 10:39, but I'm going to shorten the break up because I don't want to short the presentation on biological conversions and interpretations of the model's outputs. That's a really key piece. So let's all take a minute to maybe get a little refreshed. We'll take a stretch of the legs, and we'll see you back on here at 10:45 West Coast time, or in 6 minutes anywhere else. Take care.
Thank you.
Okay. Let's start recording the meeting again, and I'll hand it off to Martha, who's going to introduce Christina Frieder.
Okay, well, actually, I believe you just did. And so, Christina, if you would go ahead and share your screen. So we're running up to the last talk of the day. And Christina is going to be talking about our biological interpretation toolkit. Take it away, Christina.
Okay. Thanks, Martha, and thanks everyone for being here to listen about how we're taking the extra step of going from the ROMS BEC model output to making additional interpretations as it relates to oxygen loss and acidification for some of our applications. So Jim and Curtis just really nicely laid out the ROMS BEC model and how it predicts chemical changes to the oceanic environment, but what the managers want to know is how that impacts marine life. And so while the BEC component of the model has lower ecosystem and changes in phytoplankton, it doesn't make predictions on fish or other aerobic organisms, other taxa that are of either ecological or economic importance. So that's what we've been tasked with, is to develop a framework that translates seawater chemistry changes that are predicted by ROMS BEC into their biological effects. The basic framework that we started with here is that you're challenged with this model, and the model output is at such a high density of data. There's tens of millions of grid cells, so you can have predictions and changes in chemistry that amass to that amount. And so how do you collapse that into information that is biologically relevant? And the way we've approached this is to come up with a way of characterizing changes in ocean chemistry as being either as offering either habitat to organisms or being uninhabitable just based upon their conditions. And so what we need to do is come up with biologically informed metric thresholds that allow us to translate the model into a metric that says something about habitat availability. So the goals of my talk for you guys is to first describe what approach was taken to derive biologically relevant thresholds that were for both oxygen loss and acidification, and then to demonstrate how we apply those thresholds to model output, thinking about what decisions are needed to apply them, and use an illustration of sensitivity analyses to show how decisions we make in the model application are for some of our outcomes. So I'm first going to start with talking about the development of acidification thresholds. You might ask, why did we develop acidification thresholds? There are existing pH water quality criteria, but we felt that the water quality criteria that exists for the ocean isn't really biologically relevant on broad regional scales. So as they exist, their waters are defined as acceptable if they span a pH range of 6.5 to 8.5, or in other areas, if they don't change plus or minus 0.2 pH units. This was really developed for sort of an end of pipe localized impact, but wasn't developed for region-wide assessments of changes in acidification. The other thing is that there really isn't a framework about how to make these assessments, and we know that pH varies naturally in the oceanic environment, particularly the depth, seasons, interannual timescales. So there was a process taken to develop thresholds based upon the past few decades of ocean acidification research, where there first was a primary literature review for key taxa, and I'll show you which ones those were in a minute, and a data collection to create a table of a data set of acidification impacts on marine organisms that scale a range of responses from physiological to growth to survival. And threshold statistical analysis was performed to identify key thresholds in some of these response measurements. So here's just one example of the thresholds that was evaluated. This one was for pteropods and looking at shell dissolution. But it didn't stop here at the statistical analysis. Then what happened is that a group of experts was brought together to go one by one through these developed thresholds and look at what was the data that went into them. Is there enough data to even evaluate a threshold? And in some cases, things were thrown out. You know, there isn't enough information here to develop a threshold. But for other types of responses, there was. And what would be the best statistical approach to identify what that threshold is? And then following on that, once thresholds were identified, the experts went through an uncertainty assessment, identifying a confidence scoring for each of those thresholds. And I'll show you what that looked like as well. So the pteropods, the organisms that were focused on, there were 3 different groups of taxa that were prioritized to go through this process. There was a focus on pteropods, which are pelagic calcifying zooplankton. There was an emphasis on echinoderms, and there was also an emphasis on assessing acidification impacts on decapods. And after going through this process, there were over 135 studies identified across these taxa that had acidification impacts on a process or a response measurement that involved the collection of over 40,000 data points. What then happened was, with the statistical threshold analyses, thresholds were identified. They covered multiple pathways of impact. They also covered different life stages, whether it was pelagic or benthic life stages of these 3 major taxa. These thresholds were reviewed then by the group of international experts. There was a different group of experts for each taxa to match their expertise. And I'll show you a subset of some of these thresholds that were compiled. So these are thresholds for all 3 taxa. You can see that the acidification metric plotted on the x-axis is pH, and across all of these different responses, the thresholds existed anywhere, say, between 7.1 and 7.9. But that there's really a clustering of responses between 7.6 and 7.90, so occurring in a much narrower range of realistic oceanic conditions. There are important differences among taxas. Pteropods came out as the most sensitive. They have very high they have thresholds where they are more sensitive to acidification than the other groups that we looked at. And in general, the pelagic phases and the pelagic type thresholds were more sensitive than those of the benthic. So this is just an example of some of the thresholds that were developed. And you can see that they span a range of, as I said, physiological through growth, behavioral type responses. But also what's really important is you can see with each one of these responses, there's an associated duration with that. And that was prescribed by the experts based upon the literature synthesis about what is the time scale over which these thresholds become important. And you see on the majority, it's from 1 week to a month time scale, which becomes important when we start to think about how to apply these to model outputs. Then there was a process for each one of those thresholds to go through a confidence rating that was done by the expert groups. And they did that for each individual threshold. And they did it adopting IPCC's approach to confidence scoring, in which there are two scales of scoring. They score the amount of evidence there is in each individual threshold, just based upon the amount of data and the consistency in the data, so that can go from low to high. And then there is the amount of agreement among studies. So there can be multiple studies assessing a single response, and how well does the outcome from all the studies agree with each other. So the higher confidence corresponds with the darker blue region of this chart. And so the experts scored each of those thresholds, which are these individual boxes, represents the individual thresholds identified for pteropods, decapods, and echinoderms. And you can see that this degree of evidence, degree of engagement, higher confidence ends up higher up on the scale, and that pteropods had by far the highest confidence thresholds of any of the thresholds across taxa, but that there are thresholds available with medium confidence that span whether you're looking at benthic habitat or pelagic habitat or particular interest in different life stages, etc. I want to transition and talking about the process to derive oxygen thresholds. You might also ask, like for pH, why didn't we use existing pH water quality criteria? You could ask the question for hypoxia. There are many thresholds abundant in the literature about oceanic hypoxia and what that value of oxygen is. And we went beyond just using standard hypoxia thresholds. And we did that for two main reasons. One, we really wanted to incorporate the temperature dependency of oxygen solubility and oxygen and metabolic rates for organisms on these oxygen concentration thresholds. Another is that there has traditionally been a focus on acute lethal levels of oxygen, so coming up with thresholds that are lethal for marine organisms, but we wanted to focus on or have thresholds that were also represented sublethal oxygen loss, because we feel that those can be much more pervasive and ecologically impactful as well. So to dive in more about why we think this temperature dependency component is so important, here I have temperature versus oxygen, and I have two different lines plotted. And the first would just show you what an oxygen threshold that is temperature independent would look like. So you would apply the same oxygen condition across all temperature conditions, versus something that is more realistic for marine organisms because their metabolic demands generally increase with increasing temperature. So the second curved line represents what a temperature dependent threshold might look like. And so how much do we think the difference in this matters? And particularly for upwelling systems, because temperature and oxygen are highly correlated, we think that this incorporation of temperature dependency and oxygen thresholds is extremely important. So I've added onto this the occurrence of these temperature by oxygen conditions in the Southern California Bight. And you can now see how a temperature independent threshold would miscategorize habitat, either false positive or false negative, and say that it's suitably habitable or uninhabitable when in fact it isn't. And so for this example, with just these example curves, you would have something on the scale of a 40% miscategorization rate about habitat being aerobically habitable versus uninhabitable to an aerobic marine organism. So what we did is we adopted the metabolic index to address these issues of variable oxygen supply and demand and incorporating that temperature dependency. This is an ecophysiological framework that was developed by Curtis and his colleagues. And at its most fundamental form, it's just the ratio of the environmental oxygen supply relative to the organismal demand for oxygen. So it's a supply to demand problem. And the parameters of the metabolic index include, they are species specific. So they are based upon experiments where you can measure hypoxia tolerance of organisms. And then it's also got temperature dependency parameters in there as well for both oxygen supply and demand. And it has important scaling as well that goes from lethal to sublethal impacts. So when the metabolic index is equivalent to 1, we consider that a lethal limit. That is when there is no longer enough oxygen supply to meet the metabolic demands. And so, an organism would no longer survive if the metabolic index falls below 1 for some given duration. There is then a second component where the metabolic index is above a critical level. That critical level will, of course, be species specific, is considered to have enough oxygen supply to meet all the active metabolic demands and support healthy populations of marine organisms. I want to make another point about the metabolic index relying on the partial pressure of oxygen as the metric of choice. We feel that this is also moving beyond, usually oxygen thresholds are thought in terms of concentration units, but physiologists are increasingly arguing that partial pressure is the better unit to incorporate for biological thresholds, because it is what the animal is experiencing, say, for example, at the gill, or where oxygen is the pressure that pushes oxygen from seawater into the organism. And the metabolic index incorporates this metric of oxygen units. We have a lot of information and a growing database of information about metabolic index traits, the traits that are used to parameterize the metabolic index for many species globally. And that data set continues to expand. And that global database is really important for providing context and confidence in how well we know metabolic traits are constrained for marine species and across different habitats. And for the California current species right now, we have representation for 15 of those species. And I've showed those on the right. Here we have all the species, their hypoxia tolerance, scaling, and I've darkened those ones that are found in the California current system. So now I want to demonstrate the application of these acidification and oxygen thresholds to our model output. And the first, I've shown you for acidification, we have 30+ thresholds that were derived through that 4-step process and scored with confidence. And so the question becomes, which one of those do we use? Which taxa do we focus on? And same with the metabolic index. Which taxa are we going to focus on? Do you focus on the most sensitive taxa? And which threshold values do you also emphasize? Do you emphasize lethal or sublethal thresholds? And then I'm also going to talk about then how we apply those thresholds onto the model output, recognizing that we have this 4-dimensional data stream of a high density data model output data set. So we chose to, for the specific application for the Southern California Bight and asking questions about changes in subsurface acidification and oxygen loss, we wanted to focus on the epipelagic environment. So we chose to make our assessment for acidification through the lens of thresholds that were developed for pteropods. This was the most sensitive of the 3 taxa, but it also represented those thresholds for which we had the highest expert rated confidence as well. And for looking at losses in oxygen, we did it through the lens of northern anchovy and the metabolic index, and through the lens of the metabolic index here as well. Northern anchovy represents the 71st percentile of sensitivity across all the taxa that we have for the California current system. So it's a fairly sensitive organism when it comes to oxygen loss. And importantly, we already have, Curtis gave you a teaser at the end of his talk about a California current example, a published case study that shows strong correspondence of the metabolic index for northern anchovy to some of its observed abundance data. So we had some prior information for northern anchovy as well to work with here. We focused in terms of what values of thresholds we chose. We focus on by choosing 2 bookended threshold values, one that represents more lethal effects and one that represents a sublethal. For the acidification thresholds, this was a aragonite saturation state for pteropods of 1.0 representing lethal effects, and then a aragonite saturation state value of 1.4 represented sublethal effects to pteropods. In terms of oxygen loss, we focused, and I kind of teased at this earlier about the importance for the scaling of the metabolic index, is that we focused our lethal thresholds on that metabolic index value of 1, where you're starting to have supply no longer meet the metabolic demands of organisms. And then we also, for our sublethal threshold, focused on this critical metabolic index value that is a species-specific value. So I want to show you an application, or I'm going to show you the application to the Southern California bite, so I can show you how we make choices about how to apply these metrics to the model. There are 2 scales of spatial aggregation. There's a vertical component, and then there's also looking at a horizontal component. At the very first, we collapse the vertical into looking at habitat thickness. So habitat thickness is just looking at the total amount of the water column that is greater than our threshold of interest, and calling that suitable habitat, whether it's relative to the acidification threshold or the oxygen threshold. And so you can see that example on the right. We apply it to all the grid cells in the model. We do this based upon the daily outputs. And here's an example of habitat thickness across the Southern California bite domain for the aragonite saturation state threshold of 1.4. And you can see it just, the overall trends follow broad spatial oceanographic patterns as well. The other thing is that we also evaluate dominant temporal scales of variability in this metric to consider then when we do applications and think about impacts of nutrients in the Southern California bite, already having context for what the dominant scales of temporal variability are. For both of these metrics, the dominant scales of temporal variability are seasonal and interannual. I'm showing here the seasonality for both the acidification, the sublethal acidification threshold, and the seasonality of the sublethal metabolic index threshold for northern anchovy. And you can see there's this compression of habitat, summer to fall, and this pattern is the seasonality is very consistent among years. That's represented by those individual light gray lines. But we also do know that interannual variability is very important. You guys have already asked questions about ENSO and marine heat waves. While seasonality is an important component, we also evaluate how consistent patterns are among years as well. So then when we now have habitat thickness that's predicted by models, for the Southern California bite, you're going to see there's this application and looking at land-based nutrient inputs to the coast. And so what happens is we have different scenarios of the ocean, ones that represent the natural oceanic environment, and another model simulation that represents the natural ocean environment plus those land-based inputs. And so the question becomes, when you have a predicted habitat thickness for one metric in scenario A and another one in scenario B, you get a difference between the two. And so here's just one difference for a given month between 2 scenarios. So what is considered significant here? How do we know what is arising from the noise? So first we do an evaluation of habitat change, identifying areas where we see persistent changes that are either recurrent, meaning they are happening on a seasonal time base, or they're persistent, meaning happening all of the time. And what we found in just going through this analytical procedure is that there is this background 10% noise in these habitat metrics in different scenarios for these types of applications, but that we have higher confidence that when habitat change is going beyond 20%, that's going beyond sort of the noise of the models. So here's an example. This is the difference between 2 different scenarios. So the difference in calcifier habitat thickness, the percent difference in aerobic habitat thickness between 2 different scenarios, looking at the seasonality of that. And you can see it mostly falls within the noise when there is no effect. but there's this strong seasonal component where you're now going beyond that 20% change. And so then we would go in and look at further into that 20% change, how what's driving that change, how extreme is it, et cetera. So now that when we assess patterns and change, we also go through a framework of sensitivity analysis approach. I've already been detailing some choices that we make along this assessment pathway. We are selecting specific values of thresholds. So how sensitive is the outcome of our findings from that value threshold choice? We also considered, okay, we focused on, especially for metabolic index, we have many different metabolic traits for California current species. And we focused on northern anchovy. What if we looked at other species? And then there's also a component of temporal and spatial averaging that can influence the outcome of our findings. So that's our general framework, is that we then go dive into each one of these. And I'm going to show you examples of this. And this is applied to our Southern California bite model output. So knowing that these sensitivity tests are then become very application specific, but this is really just to show you the framework for how we think about testing how sensitive these decisions are. What we often find is that there's very little sensitivity in our findings to the value of acidification threshold chosen, as long as it's a value that occurs in that upper in that epipelagic environment. So say between 0 and 200 meters water depth. This is often because when you see changes in chemistry that are due to changes in biogeochemical rate processes, they're happening over a broad depth range. It just doesn't happen at 10 meters water depth. It happens across a broad range. And thus it encompasses a range of threshold values. So here you can see that there's in this case a change, a negative 20% change in the depth of habitat thickness across from about 1.2, that's consistent from 1.2 to well above 2.0. I also want to highlight how sensitive we have found our outcomes to be in our choice of species. So for the metabolic index, we've been focusing detailed assessments on northern anchovy. And for marine organisms, they really exist along a spectrum of metabolic traits. And you can see that for this example, there's habitat change that spans a gain in habitat to a loss in habitat, and among species, anchovy falls within that a loss in habitat, but so do many other species. So we can kind of evaluate where they fall within the spectrum of anticipated change through the lens of the metabolic index. And then how sensitive is our outcome to scales of temporal and spatial assessment? Really, we have little sensitivity to temporal averaging from daily to monthly. I've shown you that the dominant scales of variability in these metrics are seasonal to longer time scales. But when we do see effects that are seasonal, we then have outcomes that are very sensitive to multi-year averaging. So if you just average across many years, you tend to have a dampening in the signal of the effect. And then the outcome is also sensitive to assessment of the spatial footprint of change. So what we have been focusing on is this plus or minus 20%. So here's an example of a difference between two scenarios, looking at a 20% loss in calcifier habitat thickness. And you can see how that then scales when you look at the total area covered by, for example, a loss of just 10%. We are comfortable with this 20% assessment, but it is possible that there is a scaling or about that we are being conservative in this approach and trying to identify what is really a rising signal relative to noise. And so really the next step from here is to build confidence in these sort of spatial footprint assessments of change, is to marry this with observational data sets and monitoring programs. And so that's something that's underway or has been underway and is continuing to be ongoing. is to confirm with chemical biological monitoring programs. Already we have many field-based studies that demonstrate the importance of ocean acidification and hypoxia condition for biology, but there isn't a standardized assessment of how to do that. And so the Ocean Protection Council is supporting collaboration among California's existing regional monitoring programs. So this includes Cal Coffee, this includes the Southern California Bite Program, Access in Northern California, and also NOAA's West Coast Ocean Acidification Research Cruises, to build out and sustain a coupled program for looking at biological and chemical OA impacts over these large, broad spatial scales. And this is some of what they're developing. So you can see there's a direct link with what we're applying to model output about pteropod shell dissolution, matching what is happening in these chemical and biological monitoring programs. So this is an example of collected pteropod shells up and down the US West Coast and looking at the state of their shell condition relative to the chemical environment. And that is we're hoping that these efforts will provide increased robustness and confidence in what we're applying to the model output to make these biological interpretations. And with that, I'm happy to take this into questions.
Great, thank you so much, Christina. So Kevin, we'll pass it back over to you to manage the panel questions.
Thank you, Martha. Christina, yeah, well done. Gordon, I'll turn it over to you and ask the panel if they've got any questions for Christina.
Sure, thank you, Christina, for the great talk and very interesting. So looks like Margie is ready. Go ahead, Margie.
Hi, so I have a very, very short question this time. But this is great. I'm just so impressed with all this work. All of these decisions are so difficult to make, and I think you're just doing this in just the right way, seeing the sensitivity to all of them. Just one really quick thing. When you talked about, I like the idea of this habitat thickness, and you said it was calculated over all the grid cells, and this color bar went down to 120 meters. Is that, some of the grid cells probably aren't as deep as 120 meters, or simple question?
Yeah, I'll just, I'm going to share my screen. Yeah, so you were, there certainly is, there's interaction of thresholds with the sea floor where the sea floor is shallower. And so where if these habitat metrics are occurring between 80 and 100 plus meters, there's definitely an interaction closer to the coast. And so you can see on this specific example, I've mapped the metric in parts of the ocean where the seafloor is greater than 200 meters water depth. So places where that's the contour, I have the bathymetric contour of 200 meters laid out so that you can see this analysis was performed where there is not an interaction with the seafloor because we were focused on epipelagic organisms. You can imagine a flip where you're interested in the benthic and you are interested at where these thresholds interact the seafloor. And so you could make that assessment and really focus where the seafloor threshold interaction happens. So we were really focused on epipelagic and where these thresholds are not interacting with the seafloor. And that's why there's this white space between the coastline and where the 200-meter bathymetric contour occurs.
So do some of these, the species that you're interested in though, couldn't they be very in the surface waters, but very close to shore?
Yeah, absolutely. So pteropods, we do have a lot of monitoring data from, and they occur across these broad geographic regions. And so this assessment, I'm going to be showing next, we're going to present next time about the specific assessment of land-based nutrient inputs and the broad regional patterns over which we see. So we wanted to select organisms that represented and were present in those broad regional patterns. And same with the northern anchovy. So we made that taxa selection. But you're right, you could also make an assessment of things that are very, very coastal and represent that near shore as well.
Okay, thanks.
Yeah.
Any other questions from the panel? Neil?
Hi, thanks, Christina. That it was really great to see you lay out the whole thought process of how you develop the indices, and it's really impressive. Maybe this question, based on what you just said, is better to come back to next week. But I was wondering if you've thought about ways to link this sort of the interpretation over a large area with the way that a particular species uses space. You know, there are going to be some species that advect right through the system, and where if you have, you know, a habitat gain right next to a habitat loss, you can just read that as displacement rather than, you know, a loss in a particular habitat. Whereas, you know, for a strongly contrasting example would be like a, you know, a benthic sea urchin, where, you know, if there's an area of loss that is just an area of loss. So maybe it's really a question about connectivity or something like that. Anyway, I'm just curious, have you gone down this road at all?
Yeah, so I think what you're really I hear asking is, now we have these predictions about where there are habitat changes, and the question is, does this matter for populations? So making that translation to populations, and it will be taxa specific. Can the taxa move or not? Right? So you can imagine fish swim away, but then you gave a seafloor example of an urchin can't, right? It can't possibly, it is more likely that it cannot move at the scale of maybe some of these changes. And so that's where this link to populations is the challenge, and why I wanted to bring up this next step of linking what we're seeing in the model output to this chemical biological monitoring programs. And so how much evidence is there from the natural field about when do these scales of habitat change start to become important for populations? So we're really looking for extra field support to understand at what scale these model changes, or what the model is predicting, become important.
Okay, I don't entirely see how that connection would work for a lot of populations, but that sounds like a good thing to talk through then next week. Just, you know, I'll just say the other place my mind is going is the even harder question beyond that of effects on ecosystems. Like, you know, what is the overall importance of a loss of pteropods and replacement presumably with some other kind of zooplankton? And, you know, this is a really grand question.
Yeah.
I don't know. Do you have a sense either of how to approach things like that, or how to, you know, deal with the lack of that kind of ecosystem understanding in the translation into policy?
Yeah, so so our focus, because you brought up the example of pteropods, is why is the pteropods being evaluated? Is it being evaluated from an ecological importance, and do you need to scale through the ecosystem, or is it just representative of a sentinel species of change? And so these are important continuing conversations to have, and we can kind of key to follow up on.
Okay,
Christina,
thanks.
the other thing I would add to that, Dr. Bennis, is that, you know, I think that the other thing to consider is the way in which we can use both oxygen and pH and biological indicators of those two, and the ways that they behave together to provide multiple lines of evidence. And so ultimately, you know, I think it's a question not easily answered. But if we look at the response on both of those parameters and the way that we've assessed it for both, ultimately the question is, how much does a sort of seasonal loss of habitat matter? And the anchovy provides some strengths in answering the question of importance that pteropods, even though we can guess at it, may not be quite so easy to answer. So I would encourage you to think about that, and we can talk about that more next week.
Great, thank you.
Right, looks Fei, could your question be quick? Fei?
Yes, very quick. Thank you for this presentation. I assume you're using the level 3 or level 4 100 meters resolution for your analysis. I think there's an online question as well. I asked Curtis this question about a solutions, biogeochemical solutions to the different level of the physical configurations. I think this is a re-emphasize that maybe some comparison has been done. I have not followed up on that, but in general, you kind of in your conclusion from the habitat expansion, the volume perspective, the daily to the monthly averages seems less sensitive in some way, and so that from habitat the area or volume, that's maybe true. From the organisms, different organisms, I think the temporal exposure to the different conditions may be more sensitive than the monthly averages. I think this is the first comment. The second one, you did a multi-year simulation, the year-to-year variation. I assume those interannual variability is from the boundaries as well as from the local forcings. Those are two parts, right? I think that is really good at showing this a long-term simulation, and then you get a different temporal spectrum. I think this is a really good. Seasonality is very important. But my last question, just for comments, maybe next week we can discuss a little bit more that with this high resolution, can you or have anyone has done this a land nutrients input and to test the different scenarios, right? And you did some comparison. I'm not quite sure, scenario A, scenario B, what the difference, but overall, our task is with this high resolution model, the solutions, can we look into the different land sources of the nutrient input to the system at the local levels?
Right. So my goal today was to show you the framework, for the biological interpretations. And my understanding is that next week when we meet in person, you will see the specifics, findings of this question about land-based nutrient inputs, and that effect on habitat thickness and that effect on chemistry. So you will see the solutions for this Southern California bite domain, comparing these two scenarios, land-based nutrients versus that without. So you'll get that detailed assessment. In response to your very first question was about how there has been an assessment made on the grid resolution on the biogeochemistry, and that's been published by Faisal, and so I think that we can make sure that that's shared with you guys. But those type of assessments have been made for the Southern California bite.
Great, thank you,
Can
Christina.
can you give us just 1-2 sentences summary that is how much the work and effort, how much of the difference between the different spatial resolution configurations model?
Yeah, they found that it did matter when I'm sorry, can you, yeah. So they found that it did matter for the area they focused on, which was in the Santa Barbara Channel, so a relevant region of the Southern California Bight, particularly for the nutrient flux term and at the bottom of the photic layer. So you can imagine how increasing resolution and that impact on the flux term will then impact your biogeochemical cycle, because you are introducing a different amount of nutrients that then impacts phytoplankton and the subsequent BEC model. So
Christina,
Right,
that's a good answer. And I would just add to that, that Faisal Kazuri published a paper looking at that specific question of, you know, how does it matter whether or not you're resolving mesoscale versus sub-mesoscale? And so we'll put that paper in the chat, the DOI, and it's also on your reading list.
All right, thank you very much for the discussion. I know there are other questions from the panel, I think including one from Mike in the chat. We're really running out of time. I think we don't want to encroach too much into the stakeholders Q&A session. And we still have a few minutes in the end. We'll come back to the panel. So Kevin, let's go back to you.
Okay, thank you. I think right now what I want to do is have everybody in the stakeholder group who is online who hasn't been part of the participating presenter group or who's a member of the panel or the NWRI staff. If you have questions, we have the Q&A section open. There are 5 questions in there now. I'm going to run through them from the top and I'll just kind of take them in the order they're presented. And I think Dr. Deutsch, you're the star of this show here, so I appreciate you jumping back on. Thank you very much. But the first question, before I start, I encourage everyone to include any questions you might have. We do have a few minutes here up till about 11:55 allocated for this work. So if you got a question, feel free to put it in. But again, and Martha, I'll kind of guess that most of these are going to Curtis right here. But we'll start with Andrew. And his question was the quadratic adjustment to the B coefficient or the exponent term? And I'm not sure. Yeah, no, you will probably know what he's talking about, Curtis, because I don't.
Curtis, did you get that? And I also put that in the chat to you directly, so you can read it there.
You can chat directly.
Okay, that was for the rate coefficient, not for the exponent. I think that'll answer your question if I've understood the question. Otherwise, it won't. Feel free to follow up.
Yeah,
but
we'll
also,
we'll follow up, make sure.
Okay.
Okay, good. Thanks, Suzanne. Next one, and again for Dr. Deutsch, in your sensitivity analysis, did you look at phytoplankton growth rate? And if so, what was its effect on NPP? And then the second part of that is, of the parameters tested, what was the most influential parameter that governs NPP?
Yeah, so let's see. The first part of the question, yes, we did play with phytoplankton maximum growth rate, and it had also a fairly modest, I mean, this was a few years ago, so I don't have a number in my head, but it was not, it did not have a big effect. And I think the basic intuition for that is the one that Neil identified earlier, which is that at the end of the day, you're sort of limited by how quickly nutrients can be brought back by physical mechanisms. So compared to something like, the thing that we did that had the biggest effect on overall productivity was to kind of mimic the effect of canyons at the end of the Juan de Fuca Strait. And that was actually something inspired by work that Neil had done years earlier, showing that mixing along these canyons can bring a deeper thermocline, high nitrate concentration water up onto the shelf and then have it modified in an estuary. And so adding that as a boundary condition had the largest effect by far on net primary productivity. And I think that supports the idea that really it's sort of net input of nitrate is the key lever. And if you just increase the potential growth rate of phytoplankton, the maximum possible growth rate, you don't do much if you don't also give them more nutrient to feed on.
Makes sense. Excellent, thank you. Okay, I'm going to move to the next question. And Suzanne's going to type answers, and we'll make sure that those are, we'll follow to make sure those are accurate, but I think she's trying to do the best she can. So thanks, Suzanne. Next question, I think this is probably a Curtis question, but Martha, correct me if I'm wrong, is which BEC parameters most influenced NPP? Of those most influential BEC parameters on NPP, how did a change in these parameters affect oxygen and pH levels?
Oh, Curtis.
Yeah, I couldn't give you kind of a ranked list. Sorry, it's a weak answer. But we just didn't do a numerical ranking of them. We did have our primary focus was on NPP. We did take some look at the effect on oxygen, never on pH, although the two behaviors should be fairly well correlated. And we found that the effect on oxygen was even less than on NPP, largely because a lot of the oxygen deficit that you see in the California current is brought in from elsewhere. We did quantify that with some numerical simulations. Something like 1/3 of the apparent oxygen utilization is due to respiration within the California current, and 2/3 is already arriving from the broader Pacific Basin, which already diminishes how much leverage you can have by tweaking anything that influences respiration. The NPP, of course, if you change NPP by 10%, you will roughly change respiration by 10%, but that's also spread over the water column. So you don't see, locally, you wouldn't see all of that either. So I think that's why essentially the most of these ecosystem parameters will have their most direct impact on NPP, and then things like oxygen and pH will be will fall behind by how much I couldn't really quantify for you right now.
Appreciate the response. Yeah, I think the stakeholders understand the limitations of what we can do in our research, but thank you for clarifying that. The next question, I think we're going to stay with Dr. Deutscher. How are the BEC parameters specifically adjusted for the SoCal bite versus previous iterations of the model in the open ocean and with there were different biogeochemical conditions?
Yeah, so of those 90 parameters that I kind of loosely enumerated, they are all single numbers that apply throughout the model domain. So if you change maximum growth rate, for example, of large phytoplankton, it applies everywhere. Of course, the large phytoplankton don't achieve that maximum growth rate, and the degree to which they don't achieve it varies from place to place, depending on light and nutrients and iron and all that stuff. But each one of those parameters applies throughout the domain. And often what happens, as you saw in the case of mortality, is that if you change that parameter throughout the domain, some places will have an NPP that goes up and other places will have it go down. And that's largely because, if you increase growth somewhere, you're kind of robbing Peter to pay Paul. You strip the nutrients out closer to the coast, it's going to have a downstream effect offshore that reduces nutrient supply. So if you make phytoplankton grow faster, you will increase growth a little bit right where the nutrients are coming up, but then downstream they've stripped out more, and so growth will go down. You see that kind of thing in many of these parameter settings. So really, if you wanted to do a kind of more systematic and rigorous tuning, what we looked at was just sort of overall regional changes. And if you would probably make different choices if your target was to tune NPP just in the coastal Southern California bight. You might end up with a slightly different parameter set, simply because if you optimize for that region, you're going to change something somewhere else that has a counteracting effect on the overall root mean square error. And so, our choices were basically based on what gave a kind of on looking for large scale improvements rather than local improvements.
I think that that's a great answer, Curtis. And the other thing that I would add to that is that, I think ultimately the problem with optimization is you start to depart from what you understand as mechanistic and more towards essentially trying to get the right answer, but not necessarily understanding why. And the essential function of this model is a mechanistic prediction to support water quality, which means that we need to be able to speak to mechanisms. And so I think our attitude and why we have not done any additional tuning in the bight is because unless the validation really points to a problem, we want to have harmony with our understanding of mechanistic parameterization. And the responses of the model over a large range of gradients, that are not only present in the Southern California bight, but California current wide, both local anthropogenic as well as climate change. So great answer, and I just wanted to add that to it.
Thanks, Martha. There's the next question, I think, is really a question, is really a call for some data, and we can move forward on that without belaboring it here. Also, I'll move to the next question, which is in Dr. Deutsch's presentation. We heard about the relatively low effect of light limitation on NPP. So the question is, what had the most effect, and how did this in turn affect OAH?
Let's see. I guess I just want to make sure that I didn't give any false impressions about the importance of light, because certainly light is important. There is a time scale effect. So if you say reduce cloudiness and increase surface irradiance, there is a sort of short-term response where light limitation goes down, net primary productivity goes up. What happens then, though, is that the nutricline deepens because nutrients are being consumed deeper into the better lit surface photic zone. And that will happen until the point at which there's a kind of new equilibrium between nutrient limitation and light limitation. So in the longer term, the effect of light is greatly attenuated by that in the new equilibrium, but in the shorter term, there can be a substantial response to changing light conditions. So I just wanted to clarify that, and in the process of doing so, I forgot what the second part of the question was.
Well, I think we were trying to get at what was the effect on the outcomes for ocean acidification and hypoxia?
I didn't look at that specifically, but it's a good question. And all these questions are all ones that I wish I had anticipated when we were doing this sensitivity testing, because at the time we weren't really, our focus was not on quantifying. Our focus, frankly, was on understanding interannual variability, and we just wanted to get a mean state that was a good background baseline state in which perturbations would have the most reasonable and realistic responses. In hindsight, I would have kept better track and done more metrics of exactly how each of these parameters altered some of these sort of large scale and more regional scale metrics. And it's possible that, we still have the model output that could be done to the degree that that's an important thing for us to have more quantitative answers for, that's something that could be discussed in the in-person meeting, I think.
Let me jump in here, because essentially this kind of painstaking, comprehensive, systematic documentation of parameter sensitivities has never been done by a realistic model by anyone. I mean, it's an enormous amount of labor with, essentially no payoff behind, wandering your way, through various perceived sensitivities and deficiencies until you arrive at a point where you see diminishing returns. There's a very human element to, making models.
Jim, I would agree with that. And the other point that I would make that came up during our uncertainty webinars a couple of years back is that, Chris Edwards noted that if you have 90 parameters, you can have multiple parameter solutions that in any combination that could give you.
What do you think of
good
90
answer.
factorial?
Exactly. So the point is there is no one set of solutions that is it that's exactly right. And the question is ultimately, can you justify your choices for what you're choosing to use? And a lot of them, in those cases, I think that is what we tried to document in the Deutsch et al. 2021 paper.
Excellent. I'm kind of going through the rest of the questions, and there's some that I think we can answer. There's some that I think could frankly be better, and I'm trying to figure out if we can answer some through writing some next week. If there's anything that has a particular immediacy to answer.
So Kevin, I do see one that says it's for Jim,
Yeah.
but I want both Jim and I to speak to this because I want to make sure that we're really clear, by the comment that Jim made. It says, he notes at the end of the presentation that models moving into an operational model funded by managers and not NSF. What is his anticipated timing on this statement, and can he provide more information why it's moving out of the NSF funded domain? So Jim, I'm going to give a simple answer to this, and then I'm going to ask you to elaborate because you know better than me. What I want to say is that ROMS BEC and other types of these models are community research models, and that's what Jim meant when he said this. This model is living and it's going to evolve and move on. If managers want to take this community research model and start to really require a lot of extra bells and whistles, that's not a part of the typical research activities that are funded by NSF or anything else, then that would require some extra tending to, and then we can call it an operational model, whatever you want to call it. But then if you're going to have it be management adopted, then it's going to need extra stuff that won't be supported by typical research grants. That's what Jim meant. Jim, add on if you'd like to.
Not much more, but I think, we have the community experience of numerical weather forecasting, which has largely moved out of the research mode, except for certain zealots of machine learning who are trying to push the envelope, a quarter of a centimeter. And it's not so much that you need extra bells and whistles as you need an extra labor force, and an extra, computational resource, because if it's operational, if it's relevant to particular questions, particular places, particular times, you need people to attend to those. And, that again, it's like local weather forecasting. It's a different community that needs to do that. And, somebody who wants it needs to pay for it.
Okay, good. Well, we're at about 11:49. Mr. Chair, I know we had a couple of panel questions that we kicked into the parking lot. What I want to do right now is make sure that we leave enough time that we get the panelists any questions that they want to get answered while they have Mr. McWilliams, Mr. Deutsch on with us. So Gordon, I'll start with you. And actually I'll hand it off to you and see if the panelists have any other questions for the modelers as we kind of lead into finish off this meeting and lead into next week.
Yeah, thank you. Appreciate that. So I saw some discussion in the webinar chat. Mike raised some question, and there's some answered by Martha. I've been listening to the conversation, so I have not read those. I don't know, Mike, do you want to ask your question here, or your question has been
Curtis
answered?
gave me a decent answer to it, and I can follow up with him next week.
Okay. All right. So maybe I know also we have several unanswered questions from the previous talk. Okay, Curtis. But maybe I have a couple of questions for Christina. Maybe I can ask that first, very relatively quick ones. And so Christina, the big top of factor for us for this panel is to think about the uncertainty. In your whole procedure of getting the threshold, the major step is the expert opinion, so expert input on that. I'm just curious about what that means. What is, this is new to me, expert estimate. So I assume you're going to the community, asking people working on those texts to provide some numbers on the pH value or oxygen threshold, and then you average them. I'd assume those experts, they're working on this text are at different regions, a different environment. So I'm curious that how will those experts' opinion or the different experience of the expert introduce uncertainty into this kind of estimate?
Yeah, I'll let Martha respond to that, because I was presenting on behalf of this, but I actually was I was not involved in the threshold derivations approach. So Martha, do you want to respond?
Yeah, so if I understand your question, you're basically asking, how does the selection of the expert, how was that done? How did they sort of weigh in? And then ultimately, how would that affect sort of the uncertainty and the thresholds? And so to answer the first question, what we did was we looked comprehensively at who was publishing experimental or field studies that really spoke to the major pathways that we wanted to capture. And we cherry picked the best of those people in order to bring them to our offices here in Southern California to weigh in. And so we typically, you can see the composition of those panel members in each of the published papers, Bedarznik et al., 2019, 2020, and 2021, for pteropods, echinoderms, and decapods, respectively. You can see the who's who, because we published it with them. And then the second question is ultimately, I think what typically happened during the workshop is that we had to get the panelists on board to understand what were we trying to produce in terms of a key graphic. And then, they had, once they understood what we were going for, then they had a very, I would say, heavy hand in curating the thresholds to make sure that we could separate the wheat from the chaff, to get rid of the junk. And so ultimately, then what you are seeing in terms of the final thresholds are ones in which they argued extensively about, to be able to give you sort of that final answer, and including the confidence. And so, they were self-aware enough to understand that there's uncertainty in that, and that's why they felt it was so important to rate the confidence. So they're essentially telling you or communicating to you about that uncertainty that they had in that threshold by giving it that IPCC designated sort of scoring. So I would look to that in particular to sort of communicate their collective feeling about that uncertainty. I don't know how adding another expert would have changed the outcome. My sense is not much.
Great, thank you for the explanation. Any other, I know there's some questions that had not been answered, question to Curtis in previous talk had not been answered. Maybe I guess before we answer those, are there any other questions from the panel at this point?
This is a Fei. there's so many people involved in this particular modeling efforts. You know, the UCLA team, the physics, you know, Curtis, the biogeochemistry, and then you got this a group, the Southern California, the coastal water research projects, and so it seems one of my general question is really how this collaboration between the academic and then a more specific targeted application of the model, how this collaboration works in terms of the model sharing. It seems so far you're focusing on the publishing in the literatures, which is, you know, that is academic standard. You publish it and accept it in a way advanced. But how does model development get into this really operational a solution or more specific tasks instead of just publishing papers? And so this is I'd like to figure it out how does the human components and the collaboration and management. So
Curtis, could I take that question?
I was relieved to see Jim's hand, but either of you is fine with me.
Oh, I didn't see you, Jim. By all means, go first. I'm happy to answer it as well.
If there are shared grants between the operations people and the science people, if the science people are making better models and the operational people have to keep up, it works.
Yeah, I think that my answer is a compliment, which is to say, thus far, you know, the science, as Jim says, operational, but I'll call it model management translation, has gone seamlessly hand in hand. And we have not, since, you know, the original set of publications, PNAS 2021, everything you guys have been given to read, there have not been any model updates. There's only been one single model version that's been employed to date.
It's ready for you.
That is going to change. And so that would be a great landing strip for panel recommendations on how should we handle that going into the future to make sure that we keep a tidy house and that we also are able to, if we do have a management accepted model, how do we keep it up to date with scientific innovations without necessarily having to spend all of our pennies on model validation every time we do it? So that's a handoff back to the panel.
Yes, indeed, it's a very good one too. Thank you. That kind of does hit on our third question, and I think it's a really good spot to end today. I really appreciate everyone's ability to contribute today. Dr. Deutsch, appreciate you being here, and appreciate you being here as well, Dr. McWilliams. All of our panelists, thanks for making time out of your day. I want to say thank you to Dr. Frieder too as well. I appreciate you being here. And Martha, great job pulling the presentations together. The staff at NWRI has been working closely with Martha to make sure that we've got a great agenda, a productive agenda for the team next week. We're gonna look to do a couple of things. We'll answer any questions here in the chat that we can answer with document distribution, make sure that gets out to everyone. We're looking forward to the 17th, and there's going to be a lot of information that NWRI will be transmitting to this group of people who are on the call still now over the next couple of days related to the logistics, the agenda, and related stuff to our live meeting for next week. I'm really looking forward to seeing everybody here in Southern California. We've got a busy week, a busy couple of days rather planned, but I'm looking forward to a productive time and looking forward to us getting a chance to kind of start digging in and answering those questions under the intrepid leadership of our chair. So, Gordon, I'm looking forward to seeing you all here next week. Any closing thoughts from you before we close the call?
Yeah, just want to thank everyone for attending this. It's a great discussion we have had, and look forward to meeting everyone in person next week. And so, Kevin, would you mind to stay on the, do you have time for a couple of minutes?
Yes, I think we should stay on and talk about the agenda and other things. And with that, what I do is I'd like to say once again, thanks for everybody for participating today. Thank you for supporting NWRI. We look forward to seeing you here in Orange County next week. And if we don't see you, we'll see you online at that time. And take care. Be safe. Safe travels to everyone. We'll talk soon. Bye-bye.
Bye-bye.
Bye.
Thank you.